Hey everybody, I want to talk to you about p-values. This is the big video for hypothesis testing. I have another video on doing some hypothesis tests, although there's an example in this video as well. And then we're also going to have one more video on why we compare p-value to alpha rather than to beta or something else. And you'll see that in a separate video. But this one has plenty in it, so let's get started. So before we do anything else, I want the main idea of p-values and the definition. Now, your book does something that is very strange, and they don't have the definition of p-value just in a box somewhere, I believe. So here it is. So firstly, p-values are how we make decisions in hypothesis tests. If you remember, at the very beginning of the intro to hypothesis testing video, I said that we quantify our data we quantify how likely it is that we would see our sample and use that to make a decision about which hypothesis we're going to support. P-values are how we do that. P-values are the probability of something, which we will see. So here is the definition. Now, I will say this. When I first started working at SBCC, I worked in the math lab quite a lot, just tutoring students. And at the time, I didn't really know much about statistics. And by far the most common question that you get if you work in the math lab and you're doing statistics is, how do I calculate the p-value? Like, that is the number one question by a huge margin. And when I first started working there, I didn't actually know what a p-value was. And so I would ask the students, okay, well, what's a p-value, so that I can help them calculate it. I don't think anyone was ever able to correctly tell me. Pretty sure that that's the case, that in the probably hundreds of times that I have been asked, how do you calculate the p-value? And I responded with, well, what's a p-value? Pretty sure nobody knew. That is not great. So here is what a p-value is. Firstly, p-value goes with an observation or a data set or a statistic. So it's the p-value of something that we gathered, some data that we gathered. It's the probability of obtaining that observation or one that is at least as extreme, assuming that the null hypothesis is true. So I'm well aware that that definition is dense and long. So we're going to go through it a piece at a time. And I want to start with the end, where we assume the null hypothesis is true. So everything we do to calculate a p-value starts with the assumption that our null hypothesis is true. Now, we'll eventually decide, based on how big the p-value is, whether we think that assumption is correct or not, but that's the assumption that we make to start. We do that for a variety of reasons. One of them is that we need to do it. We need to have, well, you'll see when we get a little bit further, but we need something to base our probability on. And so we would have to assume that either the null hypothesis is true or the alternative is true. We choose to do the null being true, which you'll see why when we go a little bit further. The second thing I want to mention, p-value is a probability. All probabilities are between 0 and 1, or 0 and 100% if you prefer. So it's actually fairly easy to mess up somehow and get a probability or get a p-value that is bigger than 1 or smaller than 0. It's actually relatively easy. Like if you calculate it backwards, like if you put in your limits backwards in normal CDF, if you do normal CDF, like how you put in left edge, right edge of the area you're looking for, if you accidentally switch them, your calculator will give you a negative number, which is obviously not an area that you can have, or a probability or a p-value. So that actually comes up reasonably often. And it's also actually pretty easy to get a p-value bigger than 1, especially if you're doing a two-sided hypothesis test, one that has a not equal to alternative hypothesis. You end up doubling something and you calculate it, you sort of shade the wrong way and then double the wrong thing. It's pretty easy to go over 1 as well. So keep in mind, your p-value should never, ever be below 0 or above 1. No matter, if I see something on a test that says my p-value is, 2.3. It's like, no, it's not. I don't know what it necessarily should be, but I don't have to do any more calculations to know that that is not a correct p-value. P-values are always between 0 and 1. The last thing to see is sort of the middle of this of the definition here, that the p-value is the probability of obtaining the observation that you got, or one that is at least as extreme. That is, I didn't, let me fix my typo here. Might as well fix it while you're watching, right? One that is more extreme. That is more extreme. There we go. So this is actually a thing we've been doing. I've been setting this up for a while now. This might sort of ring a bell from last topic, right? From topic 10 or topic 9. This is 10. So extreme in this context means further away from the hypothesized parameter value, whatever that is. I'm sorry, my mouse is not what I'm doing what I want there. Sometimes that's in both directions. If you have a not equal to in your alternative hypothesis, sometimes it's in just one direction, greater if it's just greater than or just less than. We've seen all this in writing hypotheses, right? So extreme means further in the direction of the alternative hypothesis, essentially, is what is extreme. So this is what I've been having you calculate in topic 9 specifically, right? I asked a bunch of times, what is the probability that you would get another sample that is at least as far away from the mean as the one that you saw, or as the one that you got, right? That I would imagine that sounds somewhat familiar from topic 9. The reason I was having you do that is that those are p-values, like that's what you're calculating. And so that's why I've been setting that up. So it's not different than the things we've been doing. You've already actually done this several times. Okay, so here is how we use p-values to make decisions, or I'm going to run through like how to do a hypothesis test, essentially. So, and we'll talk about where the p-values show up at the end. So here's a quick review of hypothesis testing logic and how it works. We're going to make hypotheses. We're going to have a default of the null hypothesis. If our sample that we gather is far enough away from what we think the null hypothesis is, or what we have said for our null hypothesis, then that makes us want to reject the null hypothesis. So far enough away is p-value. That's how we measure how unlikely a sample is. I just realized I'm on the header there. That's how we decide how unlikely our sample is by calculating the p-value. And that's our measure of extremeness of the sample, which I will talk more about in the video, why we compare p-values to alpha. Okay, but let's go over this again. I hate that it says my name there because I created these things. It's super annoying. Okay, there we go. So here's how we do a hypothesis test. First, we make hypotheses. We make null and alternative hypotheses. It's always the first step. For purposes of calculating the probabilities, we assume that the null hypothesis is true. That's necessary for calculating our probabilities. It's how we remember that that's part of the definition of p-value. We start with the assumption that the null hypothesis is true. And so that's what we assume is true. Then we gather our data. Now, for us, we're probably just going to read it off of the page or out of the book or whatever. If you were actually gathering a sample, this is when you would go get your sample. Now, the thing you want to know about the sample that gets a little bit where you can get a little bit lost is the sample is reality, right? That's the thing that's actually true. Now, you can be misled by funny samples, but the sample that we get is our representation of objective reality. It is not the thing that we think is true that we put in the hypotheses. The thing that is true is the sample, right? That's real. We're going to judge whether we think the hypotheses are true, specifically whether we think the null hypothesis is true, based on the sample. Yeah, so we assume that the null hypothesis is true. We don't really believe that. We're just kind of making that assumption so that we can calculate the probability, or our probability, which is the p-value. So the sample is objective reality. Don't forget that part. The sample takes precedence over whatever we think, right? The sample is what's going to determine what we believe. So once we have taken our sample, we find the distribution of the relevant statistics, so the sampling distribution of the relevant statistic, assuming the null hypothesis is true. This is called the null distribution for what I hope are obvious reasons. And this is the sampling distribution that we're going to be using to calculate all of our probabilities, specifically the p-value, right? And it's for this reason that we have to assume that the null hypothesis is true. The null hypothesis being true will give us a value for our parameter, right? Our null hypothesis is going to be something like mu equals 10, right? And so it's going to give us a value for our parameter. And that value for the parameter is then going to suggest a particular sampling distribution for the statistic that we're finding. That's how we get our sampling distribution, is with the assumption that the null hypothesis is true. So we need that. So once we found the null distribution, then we evaluate how unusual our sample was. So by using the null distribution, that's the part where we are assuming the null is true, right? By calculating our probabilities on the distribution that assumes the null hypothesis was true, or that comes from the assumption that the null hypothesis was true, that's how we are using the assuming the null hypothesis is true part of the p-value definition. So on that distribution, we find the probability of getting our sample, or one that is more extreme, exactly like we did in topic 9, right? We find the probability, like we just shade part of the distribution and then find that area. That's our p-value. So that area that we shade in is the p-value. Now, if our sample is very unusual, that is to say, it has a very low probability of occurring on that null distribution, this makes us want to reject the null hypothesis, because it seems like reality, which is represented by our sample, and the assumption that we made to begin with, the null hypothesis, disagree with each other. What that means is low p-values mean that if the null hypothesis is true, then the probability of seeing the sample that we saw is very low, right? That means if the null hypothesis is true, then we got a very weird sample. Makes us think that the null hypothesis then isn't true, because remember, the sample is reality to us, right? The sample is like, that is our representation of objective reality. If that is unlikely to occur given our assumption, then our assumption is the thing that's wrong, right? That's the logic of hypothesis testing. So if our p-value is small enough, then we want to reject the null hypothesis. So let's see what small enough means. Oops, where's my mouse? Okay, so if our p-value is low enough, we're going to reject the null hypothesis, and that's how we make our decisions. So low enough in this context means smaller than the significance level. And I have a whole video on why we compare the p-value to alpha. For right now, just trust me that we do. And if the p-value is smaller than alpha, then we reject the null hypothesis. If it's not, then we don't. That's how we make our decisions. We literally just say which number, is this number smaller than that number? By the way, let me recommend that you say it, is the p-value smaller than alpha? Because the answer to that question is the same as, do we reject the null hypothesis, right? Is the p-value smaller than alpha? Yes, then yes, we reject the null hypothesis as well. Is the p-value smaller than alpha? No, then we do not reject the null hypothesis. We go with the default of the null. So p-value smaller than alpha, reject the null hypothesis. That's the essential upshot here. All right, let's do an example. So Anna is my sample pollster here. She's polling for Randy Rouse, a Santa Barbara mayoral candidate who I've been seeing tons of ads for on YouTube. She wants to test whether a majority of Santa Barbara voters will vote for Mr. Rouse. She polls 138 likely voters in Santa Barbara, and 71 of them say that they will vote for him. So we want to test whether a majority of Santa Barbara voters will vote for Mr. Rouse using these results, 71 out of 138. Okay, now to do that, we need to do a few things. So I'm going to start by doing the thing that I said we always do first, which is write our hypotheses, right? So our hypotheses are just the mathematical version of the thing we're trying to test. Test whether a majority of Santa Barbara voters will vote for Mr. Rouse. So I want to test to see if the number of voters or the proportion of voters is at least 50% who are going to vote for Mr. Rouse, or a little bit more than 50%. So my null hypothesis, oops, I want to do this in blue. I don't know why, I just like black for the headers and blue for the writing. So my null hypothesis is that something is less than 50%, and my alternative is that it's greater than. Remember, the thing that you're testing to see if it's true is your alternative hypothesis, not your null hypothesis. The null hypothesis is the wet blanket hypothesis, right? So the proportion of Santa Barbara voters who will vote for Mr. Rouse is greater than 50%. Or 0.5 if you prefer. Either one is totally fine. I really don't care which way you write it. The null hypothesis with that is that the proportion of Santa Barbara voters who will vote for Mr. Rouse is less than or equal to 50%. Right? So those are the hypotheses. And in this case, extreme is going to mean to the right. And we're going to be calculating it with the binomial distribution, right? Because that's the distribution that we're on here. Yeah, let's go look at the next page before we do that, before I get too far off track. So find the null distribution. So this is a binomial question, right? It's a yes or no, answers are independent, meets all the requirements. So I need to find the binomial distribution. So this is going to be binomial. Oop. Oh my God. All right, I have to redo that. I'm sorry. I can't live with that B. B. There we go. Binomial. We have n equals 138. And then P, the probability of success. Well, it might not be obvious what the probability of success is here. However, remember our hypotheses are that our null hypothesis is that P is less than or equal to 50%. We're going to use that equal to, because remember, we're starting with the assumption that the null hypothesis is true, right? And so this, by the way, is why the equal sign has to go in the null hypothesis and you can't have it in the alternative, because the value of the parameter that we are choosing to assume is correct has to have the equal sign, and we're assuming the null hypothesis is correct. So that's where the equal sign has to go. I don't feel like I said that great. I hope it was clear enough, but it's like, because we are trying to get a single distribution, that's why we have to have the equals in the null hypothesis. So our null hypothesis is that essentially P equals 50%. This is 0.5. And I know that our null hypothesis actually says that P is less than or equal to 0.5. I don't know if you remember back from the hypotheses video where I said it was mathematically fine to just write all your null hypotheses as equal to, but I found it conceptually not great, right? Like we would have P equals 50% and P greater than 50% be our two hypotheses, but that doesn't cover the chance that P is less than 50%, right? That's just not even represented here. So the thing we end up using is just the equals, right? We always just use the equals to give us the value of or the assumed value of our parameter. And that's why it's okay to write just P equals 50% if you want, because that's the only part of it we're actually going to use. I still like to do it like this: P is less than or equal to 50% versus greater than 50%. Just to cover all the possibilities. It makes for a conceptually nicer set of hypotheses, I think. But the only part we're actually using is the P equals 50%. So P is 0.5, N is 138. And I want to know what the probability is, that the p-value here is going to be the probability that we would get more than, or greater than or equal to 171 responses, or 71 vote for Randy Rouse responses in this distribution, in the null distribution. So so I'm just going to use the calculator to calculate that. So this is 1 minus the probability that X is less than or equal to 70. To 70. Probability that X is less than or equal to 70. Let me just write that out. Make sure I'm not messing this up in my video. That sounds like a bad idea. So we could get like 70 or 71 or 72. And the ones that I want to keep are these guys. And I want to throw out those. So yes, 1 minus probability that X is less than or equal to 70. All right, good. So we're just going to go over to the calculator, which I believe I have up. In fact, I just turned it on. Cool. All right, so we're going to do binomial CDF. Well, actually, before I do that, I'm going to do 1 minus binomial CDF. Binomial CDF. Trials 138, probability of success 0.5, X value 71. No, it was 70. That's why I did all that work a second ago. And we get this 0.399, so about 40%, so 39.9%. Okay, let's go back to the whiteboard. And so this is about equal to 39.9%. So it's pretty likely that we would, excuse me, that we would see 71 or more yeses in 138 trials if it was actually the case that less than or equal to 50% of voters would be voting for Randy Rouse, or I guess equal to 50%, which is the thing we actually use. This makes us, well, let's go over one more page. I want to compare the p-value to the significance level. And here's the thing that I wanted to point out. Now, I did this deliberately. This was actually not an accident. I didn't specify an alpha in here. Now, mostly I will. But anytime alpha is left unspecified, use 5%. That's the default. It's the one that everybody uses for basically everything. Anything you want to publish in a journal, alpha is 5%. It's always it's by far the most common one. So since I didn't state it in here, we're going to go under the assumption that alpha is 5% because that's the default. So alpha equals 5%, equals 5%. P-value equals 39.9%. So is P less than alpha? P less than alpha? No. So we don't reject H naught. So notice that our data is very consistent with the null hypothesis. It does not contradict the null hypothesis, because it's quite likely that we would get such a sample, or one that is more extreme, if the null hypothesis was true, right? There's a very good chance that that would happen. So this data does not make me want to reject the null hypothesis. Now, when we're writing our conclusion, I want to remind you of the great Spider-Man axiom, which is, with great power comes great responsibility. And when you're writing, and with that in mind, when you're writing your conclusion, write it so that anybody can understand it. So it needs to be written in plain English so that, for instance, let's say Randy Rouse, for instance, doesn't know statistics and therefore wouldn't know what "don't reject the null hypothesis" means, right? Anna needs to tell him and other people working on this campaign what the results of this poll mean in plain English so that they can understand it. Right, so I'm going to type this, I think, text. All right, so our conclusion is that this poll does not provide significant evidence that a majority of voters will vote for Mr. Rouse. Right, that is what our conclusion is. Anybody can understand that, right? Anybody reading this can understand what that means. Now, I've hedged a little bit here, and maybe I've made it not as clear as I could, because more than half of the people in our survey said that they would be voting for Mr. Rouse, but that's not a clear, it's not a clear majority, or it's not a clear enough majority for us to say, oh, well, then definitely all, out of all the voters, that's going to be the case. Because we've only got a sample here, this is not obvious evidence that Mr. Rouse will win a majority, right? This is right near 50%, and it's not far enough away from 50% for us to definitively say, yeah, he's probably going to win. So our poll is not enough evidence of a clear majority. It's maybe suggestive of one, but it's not dispositive for sure. Okay. I want to talk about a couple different interpretations of p-values, including the person who made up p-values, Ronald Fisher, his interpretation at the bottom, which is not the one that people often go with. And I want to emphasize very clearly what he meant p-values for and how we currently use them today. So one way some people like to interpret a p-value is that it's the chance of getting a sample like the one that we got, or it's the probability, I should say, of getting a sample like the one that we got by random chance if the null hypothesis is actually true. That's almost correct. It's not quite right. It's the probability of getting a sample like ours, or one that's even more convincing of the alternative hypothesis by random chance. So that's not quite right, but it's close enough if you want to think of it that way, that's good for your intuition. Another way to think of it is that it's how well the null hypothesis is supported by the data. This is less right, but also sort of a good way to remind yourself of how to use the p-value at the end, right? Bigger p-value means more support for the null hypothesis. Smaller p-value means less support for the null hypothesis. Greater likelihood of rejecting, right? So the smaller the p-value is, the more we want to reject it. The more we want to reject the null hypothesis. The bigger the p-value is, the less we want to reject the null hypothesis, is essentially how the argument goes. The most important interpretation for p-values, though, is Ronald Fisher's, which is a low p-value suggests that more attention is needed. It does not definitively say anything, really. The way he used it and what he meant it to be for was to find disagreement between whatever your assumptions are and what the data says, right? Low p-values find disagreement there. The thing you want to remember, though, is there are a bunch of unstated assumptions that we're making when we do a hypothesis test. When we find the null distribution, for instance, it is possible that the population is not, or that the sampling distribution is not distributed in the way that we think it is, right? Like, let's say we used a binomial distribution or a normal distribution, and it turns out that that's actually not the shape of the sampling distribution. Like, we could be using the wrong sampling distribution. Something could have been wrong with our sample, right? So maybe the sample that Anna took didn't do a good job of capturing the population for whatever, or of representing the population for whatever reason. Maybe it was too small. There's lots of things that could cause your p-value to be small that are not just the null hypothesis being false. That is certainly one of them, but it's not the only one. Unfortunately, the way p-values are used today, I think, is most common in, at least in academia, in journal publishing. And I mentioned in the last video on errors that if you don't reject your null hypothesis, you probably can't publish your paper. And that ends up being the focus, since a lot of academic researchers must publish, like it's an actual requirement at some at a lot of research universities, that you be publishing papers like X number of papers per year kind of thing. Like, you can be removed if you don't publish. And so it's really important for people to publish papers. And the only way to get them published is to reject the null hypothesis and have a small p-value. And so there is often this sort of desperate attempt to get your p-value down so that the paper can be published. And it's this like bright line litmus test of, if your p-value is low enough, you can potentially publish your paper, and if it's not, then you can't. And that is not healthy. Like, that's not good science. That's not what p-values are for. That's not what they were invented for. And it's really not what they do either. Like, it's certainly not bad to have a low p-value as an indicator of, I want to reject my null hypothesis. Certainly it's suggestive of that, but it's not completely dispositive. And that's kind of how we use them today. That's a bit of a problem in statistical analysis. Now, for purposes of our class, we're just going to kind of assume that low p-value means reject the null hypothesis. We're not going to look too deeply into those other things. They take a great deal more understanding than we're going to develop in this course. So we're going to, I feel a little bad kind of perpetuating the cycle here, but that is what we're going to use p-values for. Low p-value means reject the null hypothesis, and low means lower than alpha. All right, so a couple things I want to say about p-values. I'll put myself right in the title again. Let's do that. There's a common term that you will hear called statistically significant. All statistically significant means is it's a description of data that was significantly different enough from what the p-value, or from what the null hypothesis expected, that caused us to reject the null hypothesis. So if our p-value was low enough to reject the null hypothesis, then we would say that the data that led to that was statistically significant. Sometimes we just say significant and leave off the statistically part. We're doing statistics. The statistically part of statistically significant is kind of assumed. And I've got a couple things I want to mention that I said in previous videos I would talk about in this video, so I should probably talk about them. And I'm going to punt on this one. So I mentioned journals and how there's like a sort of desperation about getting p-values low. And if p-value is not low enough, then people often think of their data as worthless. Not exactly worthless, like it's worth something, but it's not publishable in a lot of cases. That is changing, by the way. There are some journals that specifically publish non-rejected p-values, just so it's out there in the public and everybody can see, oh, here was this thing that wasn't supported like that, and that can be interesting sometimes. So the dishonest version of getting your p-value down is called p-hacking. It is unfortunately a problem. Like I said in the errors video, there's a financial incentive to get p-values down, and so people will sometimes do bad science to get them down. They will, deliberately exclude things from their sample on flimsy pretexts. It will. There's actually a look up Google interactive p-hacking. Maybe I'll put it in the description, but there's a little like p-hacking interactive thing that 538.com put out. Somebody I read a lot put out. That's really interesting, where all they do is figure out which variables to include and which ones to exclude, and to get a significant or to get statistically significant data. And I'll leave you to it. But basically, the lying version of being too aggressive with your data is called p-hacking. Don't do that. It's bad. ASA here, in my third bullet point, is the American Statistical Association. They have some pretty non-traditional views on p-values. They're very, very progressive, actually, about how teaching intro statistics should be done. And I should tell you, I relied on their guidelines, partly on the curriculum, but partly on their guidelines when designing this course. We have to learn about hypothesis testing and p-values, but the American Statistical Association actually recommends that we don't teach p-values anymore, for a couple of reasons. Number one, they're too abusable by p-hacking. Number two, people often don't understand what they mean. And when I say people, I mean like people doing the research don't know what p-values are. All they know is it's some number that a computer spit out to them. And if it was less than 5%, that means they should believe their hypothesis. And that's not great. Not knowing the details like that means that there's a lot of stuff that's being missed. So many studies have been done to show that ask, like medical researchers, that literally just ask them the question, what's a p-value? And when you get that value, what does it mean? And they don't know. Like they give incorrect answers, like wildly incorrect answers, to the point where it's worrying, like really kind of disturbingly worrying. And this is after many, many, many years of teaching what p-values are and how to use them. And it's sort of not getting through. So the American Statistical Association suggests that we should probably not teach p-values anymore, and that we should instead substitute confidence intervals and effect sizes and other things, some of which we will go into in this course, some of which we don't have time for, like effect size. Instead, we're going to continue teaching p-values. It's part of the curriculum. I got to teach them to you. And we got to learn about hypothesis testing, again, part of the curriculum. But be aware that not everybody's on board with this. And in fact, the American Statistical Association is the largest professional statistical association in the United States. And they have some non-standard views on p-values that I think I might kind of agree with. And then the last one, why do we compare the p-value to alpha instead of beta? Why is alpha so much more important than beta? Remember, alpha is our significance level, and beta is not used at all. We're just going to like throw it in the trash, basically. And I'm going to not go into that here because that is kind of a long discussion that involves a fair amount of like graphs and some kind of complicated logic that I don't want. I feel like there's already enough of that in this video. So I will put that off to the why we compare the p-value to alpha video. Okay. So there's the p-value video. Let me recap. Let me just run through this stuff real quick. P-value of an observation, so it has to go with an observation, is the probability of obtaining that observation, or one that's at least as extreme assuming the null hypothesis is true, and at least as extreme means as far away from the hypothesized parameter or farther than the observation we actually got. There's a couple important parts to the definition. Number one, assuming the null hypothesis is true. So we start by assuming the null hypothesis is true. That will be true of every hypothesis test we do, by the way. We always start with the assumption that the null is true. We need that to calculate the p-value. P-value is a probability, always between 0 and 1, never negative, never more than 1. And it's the probability of getting the observation that we actually saw, or one that's more extreme. So again, extreme means further away from the hypothesized parameter value, so further away from what the null hypothesis says. And I should say further in the direction indicated by the alternative hypothesis. So when we looked at our example here, right, and our alternative hypothesis was greater than, I was only looking to the right. Right, when I did this calculation, I was only looking 71 or greater, because that's the direction the alternative hypothesis indicated for extremeness. Where was I at? Yeah. And don't get too scared off by calculating p-values. You've actually already done it several times. I made you do it in topic 9. I just didn't call them that. But that's the calculation we were doing, and that's the calculation we'll continue doing. It's the actual calculation of p-values is not very hard. It's a thing that we've done a whole bunch of times ever since topic 6, right? If you remember in topic 6, I was having you do like, what's the probability of being further away from the mean than this number that I give you? Well, that's a p-value, right? That's why I was having you do it. I was setting this up. So it's a thing you've done a bunch of times. Don't be too scared off by it. It's actually not very hard. And the way we actually use p-values is we compare them to alpha, which is if the p-value is less than alpha, we reject the null hypothesis. If it's not less than alpha, we don't reject the null hypothesis. Yeah, talked about null distributions, talked about that exactly. And then remember how to do a hypothesis test, and please feel free to refer to this. These same 5 steps are going to be in every single hypothesis test. Write your hypotheses. Find the null distribution. Calculate your p-value, often by drawing the null distribution and shading part of it. In this case, I was using the binomial distribution, so there's no drawing and shading. It's just this bit, right? Listing out the outcomes and circling the ones we want. But same idea, right? Still giving myself a visual aid, using that visual aid to figure out what the probability is that I want to find, then using the calculator to find the probability. Compare the p-value to the significance level. Is your p-value less than alpha? Was p less than alpha? No, it was not. Oh, in fact, I meant to, I forgot to do this. P-value is not less than alpha. Oh, no, that's text. That's not drawing. Stop. Okay, good. It didn't erase anything. So our p-value was not less than alpha. So we don't reject the null hypothesis. And then we want to write our conclusion in plain English. And the reason to write it in plain English is because most people don't understand statistics. And I know that you're writing it to me, and I'm the one evaluating it, and I do understand statistics. But you want to, like, how you practice is how you'll do it when the chips are down, essentially, like the old sports axiom. How you practice is how you play. So I want you to get in the habit of writing things in plain English when those things are intended to be consumed by the general public. The general public does not know what a null hypothesis is, and not rejecting the null hypothesis is not useful information for them. So you want to essentially say in plain English which hypothesis you believe. We didn't reject the null hypothesis, so we believe the null hypothesis. And so that's what we say, essentially. There's not enough evidence to suggest that more than 50% of people will be, more than 50% of voters will be voting for Mr. Rouse. It's plausible that they could, but like that's not what our data says. Our data did not provide a clear foundation for the belief that he would be well above 50%. I'll leave the interpretations of p-values. I'll leave that to your intuition. But the most important interpretation of p-values is that if they're low, that means that some sort of disagreement between our assumptions and reality has occurred. It could be that we got a weird sample. It could also be that reality disagrees with our assumptions. So p-values really represent the idea that more investigation is warranted. Or low p-values represent that. I don't want to say too much more about this. I feel like I've gone on and on about it already. So I'm going to go ahead and stop the video there. And I will see you guys in the next video.